Alright, welcome to chapter 15. This is going to be on buffers and titrations. About the first half of this chapter, we'll look at buffers and how they resist pH changes. In the second half, we'll talk about specifically what happens when acids and bases react together, more with stoichiometry though. Our first video here is 15.1, looking at the common ion effect. This is really a good introduction to what's going to happen in this chapter. Main goals here are going to explain what the common ion effect is of an equilibrium system, and also be able to calculate the pH of solutions with a common ion. So what is a common ion? Well, a common ion is an ion that is present in two separate solutions or substances. So to kind of demonstrate this, let's begin by doing what it says in the notes here. Write the equilibrium reaction for the dissociation of HF. So HF is an acid that dissociates in water and produces the H plus ion and the F minus ion. Now the next part is, if you add the salt sodium fluoride, which way would the equilibrium shift? Well, don't forget that this is a soluble salt. Anything with group 1 metals is soluble. So it's going to split apart into Na plus and F minus. So really, when you add this salt into water, it splits apart into those two ions. You're really adding fluoride ions, which will, using Le Chatelier's principle, you will add some of this. You will increase the reaction in the reverse direction, which will shift it back to the left, increasing the concentration of this and decreasing the concentration of that. And take a look, when you decrease the concentration of H+, that should make the pH go back towards 7. So when you have more H+, pH goes this way. In this case, though, if we decrease H+ concentration, it's going to shift back towards being more neutral in that direction. So anyway, adding the salt causes the equilibrium to shift back to the left. So F minus is what we call the common ion there. It is part of the acid. It's one of the products there. And by adding the salt sodium fluoride, you can also increase this concentration and shift equilibrium back. So it's the common ion there. You've kind of already seen this before. So the common ion effect is the shifting of the equilibrium as outlined by Le Chatelier's principle. Due to the addition or the presence of a common ion in the system. So we've already seen this before. Last chapter we saw for polyprotic acids. Here's an example. Let's do sulfurous acid, H2SO3. It dissociates into H plus and HSO3 minus. And then we talked about how this HSO3 minus will go on to dissociate a second time. So HSO3 minus dissociates into H plus and SO3 2 minus. Say hi, Graydon.
Hi.
Are you my son? Okay. Daddy's teaching right now. Say goodbye.
Bye.
So polyprotic acids, they dissociate in 2 steps like this.
And 2 steps like that.
Okay, go away. And anyway, the common ion here though was the H plus. Remember that in a rice table, we start with 0 of this, we gained X of it, and got X as the total amount. Well, that total amount there becomes the initial amount right here. Okay, so it becomes X right there. So the common ion in the common ion in diprotic acids was the H plus ion. Okay.
Come on. Daddy.
Oh, it's a family fiesta tonight.
3, 1.
Okay, I think the kids are in bed now. Alright, so here we go. We're trying to calculate pH now with common ions. So the goals here are to determine the initial concentration of all major species. Okay, looking for common ions there. Set up a rice table and input the correct initial concentrations. And when you set up your rice table, especially the reaction rice table, my personal preference is to set it up with respect to the weak acid. So whatever the weak acid is in the problem, set up with that weak acid HA, turn into H plus, and then A minus. And then lastly, you'll try to calculate for H plus, and then eventually turn that into the pH. Okay, so let's see a little practice problem, put it all together here. So here we're going to try to calculate the pH of a buffer solution. And if I haven't mentioned it yet, a buffer really is just a weak acid and its conjugate base. So in this case, the A minus there. And the buffer here consists of 0.0250 molar carbonic acid with 0.0300 molar sodium hydrogen carbonate here. So you can see this is the conjugate base of this particular acid over here. So the trick to these is once you identify what you have here, the weak acid and its conjugate base, is to set up a rice table. And you actually do want to set up rice tables for these as you get started here because it helps you see how they work. But the rice table is, with respect to the acid, H2CO3 will dissociate into H plus and HCO3 minus. Now our initial concentrations are given to us. Here's the initial concentration of the acid, so 0.20250 molar. H plus is 0, and what's unique now is this is not going to be a 0 here, okay? Our initial concentration is this. You do need to be able to see this in your head by now at this point here, so take a look at it. Sodium hydrogen carbonate, because it's made of sodium here, it's soluble, and it breaks apart in a 1-to-1 ratio of sodium, and the second ion is hydrogen carbonate. Because of the 1-to-1-to-1 ratio, this is the concentration of both things, but it's really the concentration of this hydrogen carbonate we care about. So that goes in right here, 0.0300 molar. Now which way will this reaction shift? Well, if you take a look here, there's a 0 here. These two things can't collide and go backwards, so the shift is going to be to the right. So we're going to lose X, gain X, gain X, and our equilibrium will now be 0.0250 minus X, X, and 0.0300 plus X. And once you have equilibrium, set it equal to K. In this case, we're going to do Ka, because we have a weak acid here. Ka for this acid we can look up, and the Ka for this acid is, well, it's carbonic acid, H2CO3, so let's try to find it here. And there it is. So H2CO3 is 4.4 times 10 to the negative 7. 4.4 times 10 to the minus 7. Now this equals the products of reactants. It's no longer x squared on top. It's going to be x times 0.0300 plus x divided by 0.0250 minus x. So is the products here divided by the reactants. Okay? Now, what's going to be helpful here to us is the fact that K is small and X's here are negligible when you add them to other numbers. So this X right here is not negligible because we're not adding other things, but it's a small number added to this, it's negligible. And it's a small number subtracted from 0.025, it's negligible. That really simplifies the problem now. Because now what you have left here, I'm just going to kind of cross this out to make it a little bit easier here. X times this divided by 0.250. So essentially, we're going to multiply these together, and now we're going to divide by 0.0300. And when we do that, these are gone, these are gone. X is equal to that math I just said there. Multiply those, divide by this. So in this case here, X is equal to 3.7 times 10 to the minus 7. That's what X is equal to. And the nice part here is that X is equal to, right there, it's equal to the H plus concentration. So that's our molarity here of H plus. And then from that, we take the negative log of it, and we find out that the pH is equal to 6.44. And that is our pH there. And notice how it's a little bit closer to the neutral area of pH 7 there. That'll be important as we go forward talking more about buffers. Okay, so to kind of recap, these problems are very similar to previous problems we've done. The big difference here is now we don't start with 0 and 0 for our products. We actually start off with a certain concentration of the conjugate base in this case here. And problems is solved very similarly, but it's not x squared anymore. And basically, x is negligible here and here. And it's just doing some algebra to solve for x there. And these problems here, x goes back and equals the H plus concentration, allowing us to eventually find the pH. All right, this is the common ion effect and doing some calculations with it.